Okay, good morning. In the last class, we have seen the selective laser sintering. So, we have discussed the basic procedure, how a selective laser sintering is being done. And this was a figure. So, basically, what is happening is we are giving, there are two cylinders, right cylinder and left cylinder, like this. So from one portion, what is happening is we are keeping the metal powder and metal or non-metallic powder, which is to be melted or sorry, not melted, which is to be sintered to form the layer. And in the another cylinder, where the product is being produced. So layer by layer, we are producing the particular product by sintering process, and the sintering process is being done by irradiating the layer with the help of a laser. So this was the basic working. Now regarding the advantages, disadvantages and all. First of all, okay, you can see the advantages. So what is the advantage? Advantage of the selective laser sintering. First one, the process is quick. So this is quick process, and it will be able to produce complex parts which are more durable and provide better functionality. So complex products can be developed with more functionality and durability. More durable and functionality. Second one, regarding the production rate. So fast build time or the production time is production rate is fast. So fast build time or production rate. Third one, variety of materials can be processed. So through this process, selective laser sintering, you will be able to produce a variety of products. So variety of materials can be processed. Next, the raw materials used. So the raw materials used for this particular process will be inexpensive. Usually inexpensive materials, either it is metal or non-metals, it will be inexpensive. Then simultaneous production of work is possible. Simultaneous production of work is possible. So simultaneously you can have different operations in the same work. So it is possible. So these are the main advantages of selective laser sintering. So selective laser sintering means using the sintering process of the metal or non-metallic powders. So we take the non-metal or metallic powder, sinter it using the heat produced by the laser in a selective manner. So that is a selective laser sintering. And through selective laser sintering, we have these advantages. That is, first one, it is able to produce a products which is complex, more durable, and having wide range of functionality. And next, it is very fast, fast build time or production rate is very fast. Then regarding the range of materials, a wide variety of materials can be processed using this particular process, that is selective laser sintering. Then regarding the raw materials, the raw materials used are not expensive, inexpensive. Then fifth one, it is simultaneous production. Simultaneous production is possible. So these are the main advantages. Now coming to the disadvantages or limitations. What are the limitations? So though we have many advantages, we have certain limitations also for the particular process, that is selective laser sintering. So we'll see what are the main disadvantages. First one, the parts produced, the which all parts produced or the final product produced may have a rough or porous surface. So usually it have a rough or porous surface, and so the surface finish is not good. Surface finish is not good. So this is the first limitation. It is having a rough or porous surface. That means it will be having a bad surface finish. Next, there is the regarding the shrink rate. Shrink rate means usually after casting and all we have seen. Once it is cooled, what happens is the material will shrink. So likewise, here also the layer by layer we are creating by the application of heat produced by the laser, not melting, but still we are sintering the material or the metallic powder to obtain the desired shape. So after cooling, what happens is there will be a shrinkage. So the large shrink rate of this particular process, it will increase the tendency for warping. Warping means effect. One surface under first surface, over that another surface is created which is contracting. Contract there is a possibility of warping. So there is a second limitation or disadvantage. That is a large shrink rate. Large shrink rate of the process, that is selective laser sintering, increases the tendency for the tendency like a spelling under handwriting tendency for the prototype to warp. So next is regarding the material changeover. So compared to stereolithography apparatus and fused deposition modeling that we will discuss in the next topic. So comparing to those processes, the material changeover will be difficult. So material changeover changeover is difficult in this process compared to fused deposition modeling or stereolithography apparatus. Now one more, that is after the process. This is not the single process. After the this particular process, that is a selective laser sintering, we have to have some post processing also. Post processing means after this, if we want to have the final product, we have to do some more operations. So that is a post processing, like finishing operations. Some finishing operation needs to be done in order to get the final product. So that is some post processing required. Post processing required. Post processing required, or post processing or finishing operation required. So these are the disadvantages or limitations. So first one, through this selective laser sintering, we are getting a rough or porous surface. So we can say the surface finish is bad, or we are not getting a good surface finish. Next, regarding the shrink rate, due to the large shrink rate, what happens is there is a tendency for the prototype to warp. ചുളുങ്ങി പോകാനുള്ള ടെൻഡൻസി ഉണ്ടാവും. നെക്സ്റ്റ്, റിഗാർഡിംഗ് ദ മെറ്റീരിയൽ ചേഞ്ച് ഓവർ കമ്പയർഡ് ടു fused deposition modeling and stereolithography apparatus, this particular process have a difficult material changeover. And finally, we see regarding the post processing, that is for getting the final product, we need some post processing or finishing operations to be done. Now we will see what are the main materials which can be used for the process. Mainly three. First one, polyamide, then polystyrene, one more, nylon. Not this much, there are many, plenty are there. These are the main things, etc., etc. So these are the materials used for selective laser sintering. So this is about the selective laser sintering. Now we'll see next thing, that is a fused deposition modeling. Fused deposition modeling. So we'll see what is a fused deposition modeling. Fused deposition modeling is nothing but from the name itself, you will get a clear understanding. Fused deposition modeling. That means we are modeling a product, or we are producing a end product layer by layer itself in the similar manner as we have discussed in the previous case. We are creating. So this is one of the type of additive principle. So it works on the additive principle, where the material is being added to produce the final product. So that is a deposition. So we are depositing something. Fused deposition modeling. So we are depositing something. How we are depositing? In the fused form or molten form. So how we melt or liquefy, or how we reach in the final product, we'll see. So there is the same thing. We have two figures shown here. This is nothing but simple thing. That is initially we have a filament. So the filament is the raw material. Using that, we are making the final product. So it is either a plastic or wax or anything like that. So that material in the form of a filament is there. This is melted. This is melted and liquefied and passed through the nozzle. And from the CAD data, so for any rapid prototyping technique, this is also one of the rapid prototyping technique. So in any rapid prototyping technique, what are the procedure? We are initially we are creating a 3D object, 3D model in the CAD. So using the CAD data, what we do is we create a three-dimensional object. Later then we analyze it layer by layer. So each layer there will be a figure. So analyzing that, it is given to the particular machine for the fused deposition modeling in this case. So this will analyze the how the first layer is. So depending on that, using this process, that is the filament is being, so you can see here using the rollers, the filament reaches the particular surface where there are many heating elements. Using this heating element, this particular filament is melted and liquefied. So as it reaches here, what happens is the liquefied wax or plastic will be available here, and it will be given to the surface where the layer is to be formed. So using the CAD data, this will be given like we write in a paper where the ink is being dropped to the surface of the paper so that you can draw that figure. Likewise, the molten material is being given. So like this, a layer is created. So first layer is created depending on the CAD data. After that, it is withdrawn and the next layer. So for next layer, what happens is the platform you can see, it will be moved in the Z direction. It can be moved downwards. So this will be stationary. So this will move downward. Platform will move down. Initially, the platform is in this particular position. So after drawing the first layer, it will move downwards with one layer distance. So this is the 4 layers already created, and the fifth layer is being creating. So after that, what happens is it will move even downwards. So likewise, it will be repeated. So this is the mainly the raw material. Usually the raw material used will be thermoplastics. Production grade thermoplastics will be used. So this is the basic working of a fused deposition modeling. So now we'll see the similar manner in the earlier cases. What are the advantages, disadvantages, applications, etc. So first one, advantages. First advantage regarding the strength. So using the fused deposition modeling. So using fused deposition modeling, we'll be able to get the end product with the high strength. High strength. Next, the entire process is cost effective and also waterproof. easy material change possible. Then thin parts, even thin parts, thin or delicate parts can be manufactured using the particular process, that is a fused deposition modeling. That is thin parts. Thin parts can be made. Now, regarding the tolerance, close tolerance can be made. Close tolerance can be possible. And the fifth one, this is a low temperature operation. So no extra cooling arrangements required. So these are the key advantages of fused deposition modeling. First one, the end product will be having a high strength. Then cost effective. This is very cost effective and waterproof. And regarding the material change, it is easy material change. Then regarding the thickness, thin parts, even thin parts can be made. And regarding the the close tolerance is possible. Low temperature operation. So these are the main advantages. Now we see what are the disadvantages or limitations of using fused deposition modeling. First one, main thing is the part strength, which is the advantages we have seen. It is having high strength, but while considering the perpendicular to build axis, so build axis in a perpendicular ആയിട്ട് ഇതിന്റെ strength കുറവായിരിക്കും comparatively. So part strength is weak perpendicular to build axis. Now one more, that is seam line. That is, here you can see there is a layer by layer addition just by drawing. So in the final product, we will see certain lines separating the layers. So the separation between the layers will be seen as a seam line. That is another disadvantage. Seam lines between the layers. And here the supporting or the fixture, use of fixture, anything for fixing the product or the workpiece is necessary, and it is very difficult also. So the support requirement is quite difficult. So these are the main disadvantages. First one, part strength is weak perpendicular to the build axis. Then seam line between the layers will be visible. And one more, that is the support requirement is difficult. So these are main disadvantages. Now this is mainly used in 3 type of models, creating models or prototypes. There is first one, concept models. So for creating the model, to get a concept, for communicating the design, how this design is, Like that, we have to get a concept. For getting the concept, certain models are created. Next, for functional prototypes. Functional prototypes. That means in order to test it for the functionality, different functionality, whether it is working in a particular heat, temperature, or in the presence of certain chemicals, how it may perform. So depending on that, or the for testing the functionality, different functionality, also we can create certain prototypes. That is a functional prototypes. And one more, that is a supporting parts. Support parts. Creating the support parts like jigs and fixtures and all. Jigs, fixtures, helps, etc. So these are the main applications of fused deposition modeling. So we'll see one animation for this.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.